Okay. What minimum impulse must be imparted to a football to have a horizontal range of 39 meters? So now if we look at this here, oops, our football is going to travel in some parabolic motion, giving us some final distance r equals 39.0 meters. It's going to need to travel at some with some initial velocity angled with some theta with respect to the horizontal, and its acceleration is going to be minus g the whole time. Now our impulse is delta p, which is f delta t. So our delta p is pf minus pi. And assuming, so the football would of course, or assuming that it starts from rest, that would be 0. So it's just our final momentum, which is our mass times our final velocity. Now, just to make these two coincide, right, our final velocity in this case is actually our initial velocity for our parabolic motion. So I'm just going to call this mvi to make it match up with my figure here. Okay, and then, so I'm just going to call it mvi from now on. Now, we need to figure out what our actual velocity needs to be. Well, if we look at the motion we've drawn out, we have some theta, some vi. So this is vi cos theta. This is vi sine theta. Now in the y direction, we're going to have acceleration is minus g. Velocity initial is vi sine theta. Or actually, I'm just going to call this v naught, just to differentiate it a little bit. And so we can use our kinematic equations by saying our yf is our y naught plus v naught t plus 1/2 a t squared. This guy here is 0. We can also use our velocity equation, so Vf equals V naught minus or plus AT. So that we can solve for the top of the motion, at least, by saying that our time, so if we solve for the case where Vf equals 0, then that is halfway through the motion. So we know y equals 0 at that point. So then our time is just, okay, that's not what I did. My apologies. So we could do it there, but it's actually easier just to say that we're really looking for the point where they're both 0. And then we can easily solve for our V naught this way. So our V naught T is equal to minus a half AT squared. We can take that out. And our A is minus G. So then our T is our V naught, which is VI sine theta times 2 over G. Okay. And now our time could be 0 but we're looking for the non-zero solution here. So we're going to plug this in now to our x expression. So in the x direction, we have xf equals x naught plus v naught t, and that would be the x direction. Our v naught x is vi cos theta, and then our time is going to be this 2vi sine theta over g. And our x naught is going to also be taken as 0. Our xf is what we want to solve for. So our xf is 39.0 meters. So then our v naught x, which is vi cos theta, is equal to xf over our time, which is 39.0 meters, times g over 2 vi sine theta. So we can rearrange this now to say that vi squared is 39.0 meters times g over 2 sine theta cos theta. Now if we recall, the sine of 2 theta is 2 sine theta cos theta. So then we can say that vi squared is 39.0 meters times g over the sine of 2 theta. Now if we look at this, so we're trying to find our minimum impulse that will give us this distance. And so our minimum impulse is going to be where this is a maximum, because these are all constants. So sine of phi is equal to basically minus 1 or 1. So 1 is our maximum. Alright, so sine of 2 theta equals 1 at max. So then 2 theta equals 90 degrees. So theta equals 45 degrees. But in any case, that means that our vi squared, our minimum velocity, is going to be just 39 times g. So our vi is square root of this, and g is 9.8 meters per second squared. And this comes out to be 19.55 meters per second. So our minimum impulse, which is delta p, which we said was mvi, is equal to 0.405 kilograms. times 19.55 meters per second, which is 7.92 kilograms meters per second. So now part B. So we're going to assume that contact is maintained through a delta x of 16 centimeters. It asks us to estimate the time of contact. So our delta P is F delta T, but our force is delta U over delta X, or delta U is equal to minus delta U over delta X, so delta U is minus F delta X, but we know from conservation of energy that delta KE is equal to minus delta U. So that means that our delta KE is F delta X. Our delta KE is 1/2 m VI squared. Or we could write this as P PI over 2m. Okay, so then putting these together here, this means that our F delta X is equal to our momentum over 2m, or F is Pi over 2m delta X. And then from our impulse expression, we have delta P is equal to our Pi is equal to F delta T. And, oh, I just wanted delta T, so that's okay. So then our force is Pi over delta T. So then, relating these two expressions, we have Pi over delta T is Pi over 2m delta X. Canceling the Pi's and rearranging, we have delta T is 2m delta X. So our delta T is 2 times our mass, something went wrong here. Oh, sorry, that was P squared over 2m. That's why everything kind of fell apart on me. P squared, relating these two expressions, so that our delta T is 2m delta X over Pi. So our delta X is 16 centimeters times 1 times 10 to the minus 2 meters over centimeters. So put it into the correct units. Over our Pi that we just calculated, which was 7.92 kilogram meters per second. And we can see that the kilograms will cancel, centimeters, the meters will cancel, and we'll be left with seconds. So that's good. And if we work this all out, we'll get 0.0164 seconds. checking through our solution here. The impulse is 7.92, so that's what we got. The force on the football, I didn't calculate, but our contact time is 0.0116 seconds. Was I supposed to calculate it? Oh, and average force, okay. Well, that's okay, so our average force is could be computed from either one of those expressions. So we can say it's pi squared over 2m. 2m delta x. So 7.92 kilograms meters per second squared over 2 times our mass times our delta x, which is 16.0 centimeters, times 1 times 10 to the minus 2 meters per centimeter. Get rid of those. And our force comes out to be 483.725 newtons. So again, checking the solution here. So 483.7. So that looks good. All right. So it looks good.